This conference will now be recorded.
This is a video for the Math 136 Exam 2A review. So we're going to go through the first 13 problems, or 14 problems on the first video, and then the rest of the problems will be on the second part. So let's talk about this first example here. This is solving an absolute value equation. When we solve an absolute value equation, the goal is to isolate the absolute value on one side by itself. So the first thing we want to do is subtract over that 14 to the other side. So 29 minus 14 would be 15. And then we need to get rid of this because it's outside of the absolute value, so we're going to divide both sides by 3. So we get the absolute value of 2x minus 1 equals 5. Now there's two situations where you could have an absolute value equal 5. Either the inside of this expression here would be a positive 5, or the inside could have been a negative 5, because either way that would make an absolute value of positive 5. So we set up both of those scenarios. 2x minus 1 could have been a negative 5 inside, and 2x minus 1 could have been a positive 5 inside. When we go to solve these, it's just like solving a regular equation, so I'll add 1 to both sides. Do the same thing over here, and then divide by 2. So that's going to make negative 2 and positive 3. So there are two solutions to this absolute value equation. Now you do not need to check absolute value equations for domain issues, because an absolute value is all real numbers for a domain, but you're always welcome to check your problems just because that makes you have more confidence. Now, the second example, number 2 here, we're solving a radical equation. Because radical equations have domain issues, specifically even roots, we will always check radical equation solutions to make sure that they work back in the original problem. So let's look at this one. So again, isolation is kind of the key here. So we're going to try to isolate that square root. So we're going to subtract the 7 to the other side, which would give me a 4. And then to get rid of a square root or a cubed root or any kind of root, we raise it to the power, the reciprocal of this, remember, because this is a 1/2 power when you're a square root. So if we square both sides using the power rule, we're going to get that this is just 3x plus 4 equals 16. And we'll solve this. So that's 3x equals 12 and x equals 4. Now, before I actually circle that and say it's my final answer, I'm going to plug it back into the original and do a check. What we're checking for here is to make sure that we don't get an imaginary piece underneath our radical, or we also don't want to get anything that doesn't make sense. Like you can't have a 3 on one side of the equation and a 7 on the other side. So we're just going to check to make sure everything matches. So this would be 3 times 4 plus 4 under the square root, and then plus 7 equals 11. That's going to be 12 plus 4, so that's 16 under my square root. Square root of 16 is 4. 4 plus 7 equals 11, and that is true because that is 11 equals 11. So this answer is correct. All right, let's look at number 3, which is also a radical equation, except this time we need to, when we go to isolate it, we're going to be moving that x over. So we're going to have an x on the other side of our equation. So this will be square root of x plus 18 equals 2 minus x. Now you can write negative x plus 2 if you want. I'm just writing it this way. So then we are going to square both sides. And the reason this is different than the previous example is now we're squaring a binomial, which means we have to FOIL. So this is going to be 2 minus x times another 2 minus x. So we have x plus 18 equals 4 minus 2x minus 2x, and then negative times negative would be positive x squared. We can reorganize that. So that's x squared minus 4x plus 4 on the right side. We're going to move everything over to the right side just so we can have a 0 and we can see if this factors. So if we subtract over x, that'd be negative 4 minus 1 more, so that's negative 5x. And 4 minus 18 would be negative 14. And factors of 14 that are different signs, since it's a negative when you multiply, would be 7 and 2, and they add to negative 5 if we make the 7 the negative, and the 2, the positive. So multiplies to negative 14, but adds to negative 5. We'd solve each of those, setting them equal to 0. So we get 7 and negative 2. And again, you have to check these. So here comes my check. So square root of 7 plus 18, and then plus a 7, and then equals 2. That's going to be the square root of 25 plus 7 equals 2. Square root of 25 is 5, plus 7 is not 2. That would be 12. 12 does not equal 2. So that means 7 is not a solution. Let's try the next one. This is negative 2 plus 18 plus negative 2 equals 2. That's going to be square root of 16 minus 2 equals 2. Square root of 16 is 4 minus 2 equals 2. That is 2 equals 2. So in this scenario, the 7 does not work, but the negative 2 does. Okay, let's look at number 4. This is solving a quadratic equation type. I like to call these quadratics in disguise. It looks very similar to a trinomial. The way you know it's a quadratic in disguise is if you see that the middle power is half of the original power. So 2/5 cut in half is 1/5. And what we usually do here is we let this middle variable piece equal what's called a u substitution. So we let that be represented by the letter u. So anytime we see an x to the 1/5, we replace it with u to the first power. So if you have x to the 2/5, you actually have u squared, and then plus 5u plus 6 equals 0. Notice this looks more like what we consider a traditional trinomial. So then we try to factor it using the u's. So we need factors of 6 that are same sign since it's a positive 6 and add to 5. So that's going to be a plus 2 and a plus 3. We solve both of those. That's going to give me a negative 2 and a negative 3. Now that is u. We wanted to solve for x. So we need to do what's called the back substitution step. And that means you change the u back to x to the 1/5. Now, before you go and try to solve this, because what we need to do is make it x to the first power. So the way to get rid of a 1/5 power is to raise everything to the 5/1 power. But you always need to double check to make sure that this root makes sense here, because this really is a 5th root. If this is an even denominator, you cannot solve the equation that you're looking at if the other side is negative, because an even root should not equal a negative number. So since this is an odd root, it doesn't matter if this number on this side is positive or negative, but even roots would cause that issue where we could only solve, like if this was a 1/4, you could only solve it if the other side was positive. So since everything's odd roots, we can go ahead and solve. So we're going to raise everything to the 5th power on both of these to get rid of that 1/5. So this gives me x equals, that would be negative 32, and then x equals negative, I want to say 243, but I'm going to double check myself real quick. So that's 3 to the 5th, but it's negative. Yeah, so I didn't put in the negative, but it's 243. So there are my two solutions. And technically you should check these because this is a root. So you can plug it into your calculator if you need to. So negative 32 to the 2/5 plus 5 times negative 32 to the 1/5 plus 6. You just want to verify that that makes equals 0, which it does. So just in the honor of time, since you could straight type this into your calculator, I wouldn't show all my steps here normally. So you can type both of those in and make sure that they actually equal 0. Okay, that takes us to number 5. We're looking at solving this inequality and writing our answer in interval notation. So we're trying to get, this is a compound inequality. Notice that there is 2 different inequality symbols. So the goal here is to kind of get the x by itself in the middle. And the first thing you would do is want to get rid of that 7 that's added there. So we're going to subtract 7, not from just the left and the middle. We're going to do it from all 3 sides. So that would make this negative 20 less than or equal to 2x less than 4, because 11 minus 7 as well. And then we would divide everything by 2. So it's going to be negative 10 less than or equal to x less than 2. And that would be in interval notation. Remember, you always write least to greatest, which this is written in. It's a bracket because of the equal to sign on the -10, and we would shade all the way up to a 2, but we would not include the 2, so it is a parentheses. So there is my interval notation. Okay, moving on to number 6. Solve the inequality, graph the solution set on a number line, and write in interval notation. This is what we call a less than with an absolute value, so an absolute value inequality with a less than symbol. And essentially there's two types of absolute value inequalities, and there's two special cases as well. The rule is that if you have an absolute value less than a positive number, you set it up in the following way. You take the negative of that number, the inside argument here, and then the positive of that number, and you create an in-between scenario. Essentially, negative number less than the inside, less than the positive of that number. If you have an absolute value of something and you have a greater than a positive number, you're going to be, now the way I like to think about this, the reason this one's in a string like this is because you're saying distance. If I tell someone that their distance is less than 5 away from me, they could be 5, 4, 3, 2, 1, and anything in between. So you're thinking of it getting closer to you. So you're kind of stepping towards yourself, towards the middle. Here, you're saying your distance is farther away. So like if I'm, standing somewhere and I say, you need to be greater than 5 away from me, you could go to either side of me and go out 5, and then you could shade in opposite directions. So in other words, this ends up always being shaded kind of in the middle, and this kind ends up being shaded to the outsides. So the greater than case. So this ends up giving us two different inequalities that we have to try to set up. So one of those would be that the inside is less than negative of the number, or the inside is greater than the positive of the number. That gives you those two different wings in different directions. The other two special cases have to do with what if the other side was negative. If you get an absolute value less than a negative number, absolute value can never be negative, so you can't be, absolute value cannot be less than a negative number. So this is always no solution. And the other case is if you have an absolute value greater than a negative number. Since absolute value is positive, then that would always be true. So that would be all real numbers. So these are just two special cases. So this case is the less than case with an equal to here. So we'll have brackets. So we're going to set this up as the negative of the number is less than or equal to the inside, which is less than or equal to the positive of the number. So we're solving another compound inequality here. So to get rid of the stuff that's around the x, I would multiply everything by 4 first, and I'm just going to do that on all three parts. So that would make this -12 less than or equal to 3 plus 2x less than or equal to 12. I'm going to subtract 3 now from all three sides. So that gives me -15 less than or equal to 2x less than or equal to 9. And then I'm going to divide everything by 2 to get x completely by itself. Now we do not turn these into decimals. We leave it as just -15 over 2 because that's reduced as much as it can be. And that's going to be 9/2. You do want to think of it as a decimal when you put it on the grid, just so you know where to place things. Like 9/2 is 2 goes into 9 4.5 times. And so at 4.5, we would have a bracket. And this is 2 goes into 15 7.5 times. So that would be -7.5, which is going to be in between -7 and -8. And then with x being in the middle means we shade everything in between. And then in interval notation, this would be -15/2 with a bracket up to 9/2 with a bracket. Okay, that takes us to number 7. This is the absolute values inequalities again, except this time it's a greater than symbol. But you do have to isolate your absolute value before you can determine if it really is a greater than, because if this was a -3 over here and we needed to divide that over, it would actually flip the inequality. So always be careful and make sure this is isolated first. So the first step would be to move that over by dividing everything by 3. So that's going to be absolute value of 2x minus 5 is greater than 7. Now it is a greater than and a positive number, so I have two different cases. Either 2x minus 5 is less than negative 7, or 2x minus 5 is greater than positive 7. Add 5 to both sides, that's going to make this negative 2. Add 5 to both sides, that's going to make that 12. Divide by 2, that's going to make that negative 1. Divide by 2, that's going to make that 6. So x is less than negative 1 or x is greater than 6. So less than negative 1 would be a negative 1 and with a parentheses, and we shade to the left. X is greater than 6 would be a parentheses and we shade to the right. And then an interval notation, this is negative infinity to negative 1 unioned with 6 to infinity. Okay, so that takes us to number 8, and what we have to learn is that this is a step up from any of the inequalities we've done. So far we did a simple inequality where you had just an x, and we did some absolute value inequalities which have specific rules. Once you have an x squared or higher, in other words, a polynomial that's bigger than x to the first power, or if you have an x in your denominator of your inequality, you can no longer easily solve them by just moving things around. There's no property that says if you factor everything, you can set each part greater than 0. That property is only if you're equal, okay? So what we have to do is something called the chart method. We're going to analyze, based on specific critical values, what happens on each side of those critical values. Does our inequality stay true, or does our inequality end up being false? And then that helps us figure out which regions of the number line are part of our interval notation. So the way this works is the first thing you want to do is make sure that you have 0 on the right side. And if you do, you want to go ahead and factor or break down anything on the left side. So this would factor into x minus 3 and x minus 5. And that means that we have critical values, or zeros essentially, of solve both of those. So that would be a 3 and a 5. Now, those are not your actual answers. I mean, they are part of the answer since it can be equal to 0. But what we want to do is use those as separators on our number line. So essentially what you do is you take your number line and you make a mark for each of those critical values. And you place the numbers from least to greatest on this marking system. So this would be a 3, this would be a 5. I always make note of whether or not I'm going to have opened or closed circles because that helps me know if I'm going to do brackets or parentheses, and that is an equal to, so these are both included answers. Then you write your interval notation. Remember, this is negative infinity over here. So this is negative infinity up to 3 with a bracket. In between the two numbers would be bracket 3 to 5 bracket, and then bracket 5 to positive infinity. You're then going to pick a test value for each of those regions. Now, test value, and I always mark this off so I know that this is separate from the numbers. A test value has to be a number inside this interval. So something less than 3, essentially. So I'm going to pick 0. Something between 3 and 5, I'm going to pick 4. Something bigger than 5, I'm going to pick 6. As long as your number is in the interval, you should get your answer correct. Then I always put my factors over here and I list them vertically so that I can check my signs for each of these test values. So we had two factors, x minus 3, x minus 5, and we want that to be greater than or equal to 0, which means our overall sign we're looking for at the end is positive numbers, greater than 0. Now, you do want everything to always have the 0 on the right side for this sentence to actually make sense when we label it in the chart. So now we don't really care if this is a negative 3 or a negative 2 or whatever this value comes out to. We just care about if the value is positive or negative. So 0 minus 3 is a negative value. 0 minus 5 is also a negative value. If you multiply, because that's what they're doing here, two negatives together, it makes a positive. 4 minus 3 is positive, but 4 minus 5 is negative. A positive times a negative is a negative. 6 minus 3 is positive. 6 minus 5 is positive. Two positives multiplied together is a positive. So notice this very last row is a combination of what happens after you've plugged in something and worked out all the signs. Since we wanted greater than or equal to 0, we're going with the plus cases. So my interval notation is right above us. The answer to this problem is negative infinity to 3 bracket unioned with 5 with a bracket to infinity. Now, numbers 9 and 10, I believe we're just going to build on this concept. So number 9, we're looking at one that has x's in the denominator as well as having x squared or higher. There is a little bit of difference here on how we set up our endpoints, and it's not going to really make itself apparent until number 10, but we're going to talk about it as we work through this one. So first thing is make sure you have a 0 on the right side. We do. We know it's a chart method because it has those characteristics of either an x squared or higher or an x in the denominator. So we're going to factor this down as much as we can, which I believe this one will be x plus 7 and x minus 2. So then you're going to separate. Anytime I have a fraction version, I always separate what are my critical values on top and what are my undefined, don't want to divide by 0 values on the bottom. So what would make the top 0 would be a -5. What would make the bottom 0 could either be a -7 or a +2, since there's two different factors here. Now, anytime you're talking about whether or not they're going to be open or closed circles, the bottom is always open. And the reason for that is you don't actually want to divide by 0. That's the point, is we don't want to divide by 0. The top will obey the symbol. And in this scenario, since there's no equal to, that means it's going to be open this time because of the greater than. So these are all going to be open circles on my number line chart. And you do, again, want to make sure you write them in least to greatest order or your intervals won't make sense. So -7 is the smallest, then -5, and then 2. We've determined that all three of them are open circles. So this will be -infinity to -7, -7 to -5, -5 to 2, and 2 to infinity. Notice everything's a parentheses. Let's go ahead and make a separator. I need a test value for each of these. Smaller than -7, you could do -10. Between -7 and -5, I have to do -6 unless I want to do a decimal. Anytime you go from negative to positive and 0 is not one of the endpoints, because you can never use your endpoints when you're picking, I would pick 0 here. And then bigger than 2, I would pick 4. And then we put our factors. So I had an x plus 5 on top, an x plus 7 on bottom, and an x minus 2 on bottom. And I want an overall sign that is greater than 0. Notice that we are still going to be multiplying our signs together because multiplication and division follow the same rule for what comes out positive and what comes out negative. So -10 plus 5 is a negative. -10 plus 7 is a negative. -10 minus 2 is still a negative number. 3 negatives multiplied together is a negative. -6 plus 5 is negative. -6 plus 7 is positive. -6 minus 2 is negative. 2 negatives multiplied together make a positive. 0 is going to be a positive, and a negative, and 1 negative multiplied with those would still be negative. And then for the last one, they all three come out positive. So that's an overall positive. So again, because we are doing greater than 0, we are choosing pluses again. You don't always choose pluses. You choose what this tells you to choose. Greater than 0 means choose pluses. Less than 0 means choose the minuses. So the answer here is just those intervals right up above. So -7, -5, unioned with 2 to infinity. Now this leads us into number 10, which is the harder of the three that we've got here for the chart method. This one is not ready to go yet because there's not a 0 on the right side. So your first step here is you're going to have to subtract that fraction over there to the other side so that you will be left with 0 on the right side. And then this is not ready to solve because they don't even have a singular fraction on this side. We need to get a common denominator, which just so happens to mean that you'll have to multiply top and bottom of each of these fractions by what the other one has as its denominator, what it's missing. So this is 4 times x minus 6 minus 5 times x plus 3 all over x minus 6, x plus 3, less than or equal to 0. We distribute this, so that would be 4x minus 24 minus 5x minus 15. Bring down the denominator, don't lose that. And then combine the like stuff on top. So that's -x minus 39 all over x minus 6, x plus 3, less than or equal to 0. And then I'm going to break this up into what makes the top equal 0 and what makes the bottom equal 0. Bottom's pretty easy. It's going to be either a 6 or a -3. The top, you might want, and I know a lot of times some people will say, we'll factor out that negative on top. You want to be very careful about doing that, because if you don't include the -1 that you pull out in your chart as a factor, then that messes up your whole sign chart completely. You'd be a whole sign off, which means you would pick all of the wrong intervals. So I don't actually factor it when I'm doing these. I just kind of use it and solve it. I leave that top alone. So if I solve that equal to 0, I would add over the 39 and then divide by the -1. So it's a -39. Now let's talk for a second about whether or not things are going to be opened or closed. We said that the bottom is always open no matter what. When you're doing an inequality, you do not want to actually divide by 0. The top obeys the symbol. The symbol here is less than or equal to, so the top's going to be a closed value. So when we go to place these on the number line, -39 is the smallest of all of them. And then -3 would be next, and then 6. So this is the interval -infinity to -39 bracket. This is bracket -39 to -3 parentheses. This is -3 to 6, both with parentheses, and 6 to infinity. Test values. We could do -40. Make sure it's actually moving to the left. Here I could do -5, 0, and 10. And our values are -x minus 39. So notice I'm including it with that -x, x minus 6, and x plus 3. And we want to be less than or equal to 0. So this is the first time our final sign at the end we're looking for is a negative. So what we're going to do here is we're going to plug these in and check them. Be careful with the -x. So that's -40. So that's actually 40. 40 minus 39 is a positive. -40 minus 6 is a negative. -40 plus 3 is a negative. Two negatives multiply to make a positive. -5 would be 5. 5 minus 39 is negative. -5 minus 6 is negative. -5 plus 3 is still negative. Three negatives multiply to make a negative. 0 would give me -39, -6, and +3. Two negatives make a positive. And then 10 would be negative, positive, positive, and that's one negative overall, which is a negative. So we have these two negative signs that we're going to choose since we're doing less than 0, and that would be bracket -39 to -3 parentheses, union with 6 to infinity. There's my answer.
This conference will now be recorded.
Okay, so we're looking at number 11, which is now completely something different. It says find the equation of the line through -5, -2, and -3, 5. And we want to write our answer in point slope, slope intercept, and general form. So we're going to show you how to do all three variations. Typically, someone would end in slope intercept or general form, but the good thing is if you know point slope, that kind of gets your equation started into a place where you can go to either one. So things that we need to know to be able to do this problem. We need to know how to find the slope of the line. So we have the formula y2 minus y1 over x2 minus x1. And then we need to know the point slope formula as well. So that's y minus y1 equals m parentheses x minus x1. So let's first of all call this x1, y1, x2, y2. I just do first ordered pair, second ordered pair. And let's find our slope. So this would be 5 minus a -2, because that's my y's, over -3 minus a -5, because that's my x's. So that's 5 plus 2 over -3 plus 5. So that's 7 over 2. So there's my slope. When you go to do your point slope, you can pick either of the 2 points up here to do your, because what we're going to do is these two guys are a point, and this is the slope. So now that we have slope and we have at least one point, we can write point slope. So this is, remember, part of the answer is writing your answer in point slope. So y, I'm going to use the second point. Y minus 5 equals 7/2 x minus a -3, so that'd be +3. So that's my point slope formula. Now, to get this into slope intercept, there's a couple different ways you could approach it. You could distribute the 7/2 and then add the 5 over. I don't usually like to do that if the number inside here is not divisible by this denominator. So what I usually do is I clear the fraction, which is going to be helpful because we're going to do that for the general form as well. So I multiply everything by the denominator. So that's going to be on both sides. I'm going to multiply everything by 2. So this will be 2y minus 10. Here, it does not multiply to the x plus 3 because the 2 immediately cancels out with that one, and you distribute the 7. So that'd be 7x plus 21. So in this format right here, it's really easy to get to both general and to slope-intercept. Slope-intercept means that you are in y equals mx plus b form. General form means that you are in ax plus by equals c, where no fractions are allowed. And depending on the textbook you use, usually they like a to be positive. So the x term needs to be positive. So if I want to get this in slope-intercept, I would add 10 to the other side. So that makes that 31. And then I would divide everything by 2. So that's 7/2 x plus 31 over 2. So my slope-intercept is y equals 7/2 x plus 31 over 2. Now for general form, I actually go right back to this line right here, and I take it a little bit differently. I move the x over to be with the y. So that's going to be subtracting 7x. So negative 7x plus 2y. I add the 10 over, so that would be 31. And then because there's no fraction, since I already cleared that out, I just like to fix this so that the x is positive. So if you just divide everything by -1, it just changes all the signs. So general form would be 7x minus 2y equals -31. So there's all three formats. Okay, for number 12, we're using two formulas, the midpoint formula and the distance formula. Let's remind ourselves of what those are. The midpoint formula says that you take two ordered pairs and you average them, essentially. Average means you add their parts together and cut it in half because you're dividing by how many you have, which is 2. And y1 plus y2 divided by 2. So this is -8 plus -4 divided by 2, and -9 plus 3 divided by 2. That would be -12 divided by 2 and -6 divided by 2. And then that would divide to -6 and -3. So there's my midpoint. And then the distance formula is still using two ordered pairs, but it is d equals the square root of, and this is pretty much Pythagorean theorem. So it's the difference in the side length of the x's squared plus the difference in the side length of the y's squared. So x2 minus x1 squared plus y2 minus y1 squared. So this would be, let's label these. So x1, y1, x2, y2. So x2 is -4 minus -8 squared plus 3 minus -9 squared. That's going to be -4 plus 8 squared plus 3 plus 9 is going to be 12. Oh, actually, I'm jumping ahead. Let's just write it as 3 plus 9 first. Squared. And you cannot just square root this and cancel out the squares. There's a plus sign between these. You actually have to work it all the way out by order of operations. So that's going to be square root of 4 squared plus 12 squared. Square root of 4 is 16. Not square root. Squaring 4 gives you 16. Squaring 12 gives you 144. Add those together. That's going to be 160, I believe. Let me double check that. So 144 plus 16. Yeah, and then you need to double check to see if there's any perfect squares. Obviously 16 goes into this. This is 16 times 10. So that's going to be 4 on the square root of 10, and 10 does not break down any further. Okay, kind of building on that last example about distance, this is an application of the distance formula. It says find all points on the x-axis that are a distance of 4 from the point 3, 2. So you don't have to draw a picture at all to solve this, but I like to do it just to show you how I'm coming up with the problem. So if I plot the point 3, 2, there's P. We'll call that P. We want to find points on the x-axis that are 4, exactly 4 lengthwise away from this. Now we can't drop down directly because that's only a length of 2. So that means we either have to go to the right or to the left. And we don't know exactly where those are going to hit. So we're calling these arbitrary points, kind of Q1 and Q2. And they're going to be generic. So I'm going to call them just some kind of name. So how about, well, we know it's an x-intercept because it's on the x-axis. So x-intercepts are always an x and then a 0. So both of these are going to be some kind of x and a 0. And this is the point 3, 2. And I know that my distance is 4. So let's write our distance formula. So d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And we're going to let this kind of be, and I always like to start with the variable first. So I always let whichever point has that arbitrary variable in it be my x2 or my y2, depending on if they're doing x-axis or y-axis. So my distance is 4. And then this is the square root of, so the x's would be x minus 3 squared plus the y here is 0 minus 2 squared. And in this case, because you do know the number on the other side, I would square both sides and get rid of that square root, the big square root. So this would be 16 equals x minus 3 squared. It does not get rid of these. It's only get rid of that square root. And then this would be plus negative 2 squared, which is going to be 4. Subtract the 4 over, so that's going to be 12. We can take a square root to get rid of the square. Now, anytime you physically draw in a square root yourself, you have to remember to do the plus or minus on the side that has the number on it. That's because we don't know if the number was originally positive or negative before we took this, before it got squared. So then we have to add the 3 over to finish this. So this is going to be 3 plus or minus square root of 12 equals x. I can reduce that radical. That would be 3 plus or minus square root of 4 times square root of 3. So that's going to be 2 on the square root of 3. Now that is 2 separate x values because remember we had 2 separate places we thought we might touch the x-axis. So our points are going to be 3 minus 2 square root of 3 comma 0 and 3 plus 2 square root of 3 comma 0, 2 different x-intercepts. And if you want to see for a second what that kind of estimates to, because I kind of roughly drew this as hitting 0, but I kind of noticed my line didn't stay consistent. So 2 times the square root of 3 is 3.46. So if we had 3 minus that, that's going to be like a negative 0.46. So notice it would be right over here, just barely on the negative side. If we added 3 to that, then that'd be 6.46, which is kind of out here. So it does make sense that those are the answers that we got. Okay, and then the last one for the part 1 of the video is number 14. We're going to state the domain of these functions that we're looking at using interval notation. So there's 2 things going on in these 2 functions. First of all, you can never divide by 0 because that's undefined. So we do need to figure out what values are going to make us divide by 0. The second thing is we have these even roots on top. If you have an even root, you don't want it to go imaginary because when we're talking about functions, we're talking about real numbers. So to keep this from going imaginary, we need it to not be negative underneath the radical. So we set the inside of that square root greater than or equal to 0 because it's okay if you get square root of 0 on top. It's okay if you get a positive square root on top. We do not want a square root of negative 2 or something like that. So if we solve that over, that says x is greater than or equal to negative 3. Okay, so that's one portion of our domain, is that nothing smaller than negative 3 can ever be used. Then we would factor this to figure out if there's anything else we need to consider. So factors of 18 that make negative 9 would be a negative 6 and a negative 3. So that means that if we don't want to divide by 0, we need to make sure that 3 and 6 are not part of our domain. So here's where this kind of comes in. So think about negative 3 being here. This says shade to the right because it's greater than. But if you shade to the right, you're going to encounter the number 3 and you're going to encounter the number 6. Since those are not part of my domain, we make them open circles. So we're shading everything to the right of -3 except for those two numbers. So in interval notation, that would be -3 with a bracket to 3 parentheses. Union, second shading would be +3 to 6, both with parentheses. Final one would be 6 to infinity. So there's my domain. Let's do the next one. So this one again has that square root on top, so that means that x plus 1 needs to stay greater than or equal to 0. Now if those had been cubed roots, it wouldn't matter, but if it's an even root, you need to do this. So greater than or equal to -1. Factor this. This is going to factor into, let's see, -10 and +2. Because that would make -8 when you add, but -20 when you multiply. So that means that x cannot equal -2 or 10. Okay, so start off again with -1 shaded to the right. You're kind of just putting this in a frame of reference. -2 is actually on this side. You've already excluded that. You excluded it when you shaded everything to the right of -1. But 10 is over here. So in this case, only one of them from the denominator caused a problem with our top domain issue. So this would be -1 to 10 unioned with 10 to infinity. This is not the same thing as the sign charts we were doing when we were doing inequalities. This is barely really just looking at when can you not plug something into the function because it makes it undefined or imaginary. And that's it for part 1 of this video.